Hello, everyone. Welcome to this quick and simple series. Whether you are just starting out or brushing up on your skills, then this series is for you. Let's learn RAG. Before moving on, make sure you have basic understanding of AI and some familiarity with prompts. So let's start with what is RAG. Here, RAG stands for Retrieval Augmented Generation. Now, retrieval augmented generation, which is RAG, is divided into two main components. The retriever, which has ability to extract relevant information related to the input prompt and passes it as a context to the large language model to generate desired output. On other hand, we have the second component, which is called as generator, which uses both the retrieved information and original prompt to create a final answer using a large language model. Let's look at a simple example to understand how they work together. Let's assume we have an input prompt called as what is quantum computing. If it pass the input prompt to the retriever, then it will search the knowledge base and extract relevant information or definitions related to the quantum computing, which is nothing but context. Now, this is the output of the retriever. On the other hand, once we retrieve the relevant context, we combine it with the input prompt and pass both to the generator. Generator then uses this combined information to produce the final output. If you look closely, the output generated is aligned with the retrieved context. In other words, the response is heavily influenced by the information provided in that context. Now that we have a high level understanding of what the retriever does and how the end-to-end RAG process works, let's take a closer look at the detailed RAG architecture step by step. Here is how it looks. As a first step, let's start with the embedding model. Here, first we pass the input prompt to an embedding model. The goal here is to convert the text into numerical format, also called a vector, so that system can understand and compare it. This vector will later be used to find the similar content from the knowledge base using similarity scores like cosine similarity. On other hand, we have our knowledge base. For example, full book on quantum computing. Just like we did with the input, we pass these documents through the same embedding model to convert them into vectors. These document vectors are stored for quick retrieval later. We will go deeper into how this works later in the video, but for now, just remember, embedding models turns any text, whether it's a prompt or document, into a vector, which is simply numerical representation of any given text. Moving on to the vector database, which is one of the most important component in the RAG pipeline, especially for the retriever. In our case, think this as a database where we store all the document vectors that were generated by the embedding model. So, whenever a new query or an input prompt is converted into a vector, this database is searched using similarity scoring method, like cosine similarity, to find the most relevant or similar vectors. These matched vectors are especially pieces of context that are then passed to the generator to help it produce more accurate and context-aware response. In simple terms, a vector database helps us quickly find the most relevant information for a given prompt by comparing vector similarities. With that, let's quickly move on to the next component in the RAG architecture, which is similarity search. In this step, the vector representation of the prompt is compared with all the document vectors stored in the vector database or knowledge base. The system calculates similarity score using method like cosine similarity to identify most relevant vector. The output of this step is a retrieved context vector which represent most relevant information to the prompt. These context vectors will be then used in next component, which is prompt templating. Prompt templates are nothing but predefined structures designed to handle different types of questions or user inputs. These templates systematically combine the retrieved context with the user's original prompt, forming clear and consistent input to the LLM. For example, if user prompt is, "What is quantum computing?" The prompt template might be like, "Based on the context below, answer the following question." At this stage, we can define multiple prompt structures based on the type of query, whether it's a definition, comparison, or instruction. The goal here is to build meaningful prompt which will be passed as an input to LLM model. Now, finally, let's move to the last stage of RAG architecture where we pass the context along with the input prompt to the LLM to generate a response. By assessing and validating quality of generated responses, we can iteratively fine-tune the entire RAG pipeline using trial and error approach. So, that is the high-level overview of RAG architecture from input to the final output. Now that we have seen how RAG architecture works at a high level, let's zoom into one of the most important building blocks, the embedding model. So, what is an embedding model? In simple terms, it takes text like a sentence or a question and converts it into a numeric vector. These vectors represent the meaning of the text in a way that machine can understand. Think of it as a converting language to the math, which allows us to measure similarity between sentences based on their meaning and not just keywords. Here is a basic example. If I take a sentence, "apply for retirement benefits," embedding model might turn it into a vector like 0.61, 0.12, and so on. This vector is a compressed version of sentences meaning in high dimensional space. But why do we care about this? Because once we have vector representation of all our documents, we can do something powerful. As we know, embedding models capture meaning, not just a keyword. They turn text into vectors, so similar ideas are close together. This helps RAG retrieve most relevant information, even phrased differently. Let me show you what I mean. Let's say we take these two sentences: "apply for retirement benefits" and "withdraw pension savings." Although the words are different, but their meaning is almost the same. So their embeddings will be very close in vector space. But if we compare that to "make a pasta," this has totally different meaning. So its vector will be far away. This is how semantic search works in a RAG. We match query with semantically similar chunks from the documents and not with the exact keywords. Now that we understand how embedding model work, let's take a look at some popular open source embedding models that you can use in your own projects. We will use BG small en embedding model in our code walkthrough. So now you have seen what embedding models do, why they matter, and which ones you can use, including the one I picked for this project. Now let's bring it all together with a quick code walkthrough. We will see how to load the embedding model, encode the sentences, compare similarities, and visualize them. So let's code. Let's start by loading the embedding model. For this walkthrough and upcoming project, I am using BGE Base EN, a powerful and lightweight open source model for English embeddings. Before you run this line, make sure your Hugging Face setup is ready on your local system. That means you should be logged in and have your access token configured. If you haven't done that yet, I have added a quick setup guide in the description. Go ahead and follow that first. Now let's define a few sentences, some that are similar in meaning and one that's clearly unrelated. We will pass these sentences to the model and get their embeddings. If you see, this is the embedding shape 4 by 768, and these are the embeddings for our four sentences. So, to see how similar the sentences are, we will compute cosine similarity between the vectors. We will do deep dive on similarity metrics like cosine similarity in the next video, where we will break down how these scores are exactly calculated. But for now, just remember this: similarity scores tells us how close two sentences are in the meaning. Let's also visualize how these embeddings are positioned in vector spaces using PCA. You can see that the sentences book a doctor's appointment, schedule a medical consultation, and set up a visit with physician are clustered closely in lower left area of the graph. That's because they all carry very similar meaning. Even though the words are different, the intent is the same, which is booking a medical visit. On the other hand, take a look at the red dot on the far right. I bake a chocolate cake. It is clearly separated from the other points because it has no semantic similarity to the healthcare related phases. This is exactly how semantic search works. When you ask a question, the system retrieves the most relevant content by comparing these kinds of embeddings and not just a keyword but actual meaning. And that wraps up our code walkthrough for the embedding model. In the next video, we will dive deeper into the vector databases and how similarity search actually works, along with the hands on code example. So stay tuned. I will see you in the next one.